Battery management systems are designed to ensure the safety of the battery by providing protections against a wide range of dangerous events that might happen in the system. In this next section, we will explore the key scenarios where the BMS protections are critical and how the BMS will react in case of any of these events. The most relevant dangerous events that require protections are going to be related to the parameters that we have been exploring in the previous slides, like the current, the temperature, the voltage, and the loss of insulation. Different cell chemistries and different applications will require different safety limits for these parameters, but in general, we need to have protections for any of these events that include, for instance, over temperature, under voltage, voltage, over current, and short circuit. We will explain each of those in the next slides. And let's begin with the two main voltage protections that are the over voltage and the under voltage. To start then, let's begin with the over voltage. That basically this protection occurs when the voltage of a battery cells, any of the battery cells, exceeds its maximum safe limits. This can happen because of several reasons. For instance, if we overcharge our battery, also if we use, for instance, faulty chargers, and if we have batteries that are imbalanced, all of those can cause this protection to be triggered. To prevent this, the BMS is constantly monitoring the voltage of all of the cells, and if any of these cells approaches or exceeds this upper voltage limit, the BMS will disconnect the charger, and this ensures that the voltage will not continue rising. Some of the consequences of overvoltage might include, for instance, the electrolyte breakdown, which accelerates the cell degradation. Also, some other consequences are the lithium platinum, for instance, that increase the risk of internal short circuits, as well as the potential of thermal runaway that could lead to catastrophic failures and explosions in our system. Different chemistries will have different threshold voltage. Here we have two examples of the maximum recommended cell voltages for an NMC or for an LFP type of cells. Then we have the under voltage protection, and the under voltage is then the opposite, and it occurs when a cell voltage drops below its minimum safe level, and this is often produced by prolonged use of our system, also when we are using high demand loads, and in the case of having parasitic currents in the system that continuously discharge on our battery. These conditions will cause, for instance, the instability in the electrode materials that can lead to irreversible chemical damages, and as well it can lead, for instance, to reduce the battery capacity and to reduce the battery health when we use the battery at very low voltages. The BMS also protects against this, against the under voltage, by disconnecting the load when any cell is approaching their lower voltage threshold, and again this threshold will change regarding or depending on the battery cell, the chemistry, and also the specifications of each cells will provide us what are these safe limits both in the upper side and in the lower side of it. Then we have the current protections, and we have overcurrent or short circuit protections. The overcurrent occurs when in our system, or when our system is demanding more current than what the battery is designed to handle. This can happen due to external loads that demand too much current. Also, it can happen with faulty electronic systems, or when we have those systems misconfigured in regard to what the battery is expected to, or the maximum capabilities of our battery. The overcurrent conditions are critical because when we have overcurrent, usually we generate excessive heat, and this can damage the cells and can damage the electrode materials, as well as it can compromise in general the safety integrity of the battery and the lifespan of the battery. And the most dangerous is that excessive heat that is generated can lead, for instance, to thermal runaway and increase again the risk of fire or the risk of explosion. It is important to notice that in a battery, the charge and the discharge current ratings are different. Usually the overcurrent in discharge is way much higher than the overcurrent in charge. The overcurrent protections then are implemented depending on the direction of the flow of current, as well as different protection levels are used. So we have different levels and combinations between amplitude and duration. We may have, for instance, very high current and short duration protection, or another level that will be a lower current but longer duration. And all of these will be defined according to the battery specifications. Then we also have the short circuits, and the short circuits occur when the battery is directly connected or when the terminals of the battery are directly connected between them. It means that we connect the positive terminal to the negative terminal of the battery, bypassing completely our load and our system. This is very dangerous, and this can cause, for instance, the damage in the wiring, the damage in our insulators, the damage in our fuses that might be connected, as well as this can cause internal defects in our battery cells and in the contacts and in general in our systems. The short circuits result in massive and uncontrolled current flow that generates a lot of heat, and this will cause immediate damage and affect the cells, potentially even initiating the thermal runaway event. To protect against this, the BMS is designed to react very quickly in milliseconds or even microseconds to disconnect the battery and to prevent further damage and escalation of the damage when a short circuit is detected. We also have protections for the temperature, and we have over temperature and under temperature protections. The over temperature occurs when the battery cells exceed its maximum safe temperatures, which can happen due to different factors. This can happen, for instance, if the battery is operating in a hot environment or it is very close to heat sources, like, for instance, fire or another system that is heating up. Additionally, high currents during charging or high currents during discharging will also generate heat as one of the products, because as you remember, the battery has an internal resistance, and that internal resistance will generate some heat because of the power that it is dissipating. As well, degraded cells usually has more heat production because their internal resistance is higher than new cells. Another ways of that cause or reasons why the over temperature protections is caused is, for instance, the chemical reactions within the battery that produce heat as one of the byproducts when the battery is being cycled. And another cause, it might be, for instance, inadequate cooling systems or failures in the dissipation and the thermal management system that can cause overheating. When we have cells that exceeds the safe threshold, there is a severe risk. One is the thermal runaway, to have permanent damage in the cells, but also high temperatures are directly related with the accelerated aging of our batteries, which significantly shortens the battery lifetime. So it is important to operate the battery within the specified temperature range to avoid our battery to degrade faster than expected. The BMS monitors the cell and the pack's temperatures and will respond in case of these events, for instance, activating the cooling system to dissipate the heat, also reducing, for instance, the charge and discharge rate currents to minimize the heat generation, and ultimately it will disconnect the battery entirely if the temperature exceeds the critical limits. Again, the thresholds will depend on the chemistry, on the cell, and also on the mechanical and thermal design of our full battery pack. We also have problems with under temperature, and we also have under temperature protections. In this case, these protections are triggered when the battery operates below its minimum safe temperature, and typically this happens in freezing environments at very low temperature. What happens when we operate the battery at such as low temperatures is that the chemical reactions in the battery will slow down, and one of the effects is that this will reduce the battery power output. But also this can damage our battery during charging. If we charge our batteries at very low temperatures, for instance, we have the risk of having lithium platinum, which might lead at the end to internal short circuits and permanent damage in our batteries, as well as the mechanical stress at low temperatures has to be considered, because the battery casing and the internal structures can get damaged because of the low temperatures. And in this case, the BMS prevent all of these risks, again by restricting the charging and the discharging operation when the battery falls below those critical thresholds, such as, for instance, in charging, usually the under temperature is gonna be more critical than during discharging, and it will depend on the specifications of the system. But in systems, for instance, that are equipped with thermal management, the BMS can also activate the heaters to bring the battery back to the optimal temperature range, and to habilitate and to enable the battery to work under draft freezing environments. Vehicles that are intended to work at very low temperatures are required, and it is mandatory almost to have battery heating systems to be able to use them at those scenarios. Based on this, we have explained like the different protections, current, voltage, and temperature protections. All of those will define and the limits of operating our battery safely. We define the safe operating area of our battery that at the end give us the conditions under which our lithium-ion battery can operate without compromising the safety, the performance, and the longevity of our system and our battery. This definition of a safe operating area, or SOA, it is a critical framework for ensuring that our battery will remain within the design tolerance for the parameters that we defined before. So here we usually include boundaries for the temperature, for the voltage, and for the current, and all of those are defined based on the cell chemistry and the different specifications of our design. The safe operating area may include different areas. Here we have, for instance, or we are showing some of those. First, we have the hard protection, so that is everything that is with the red shadow, and these hard protections are triggered when the safe operating area basically is exceeded, and then in that case the BMS completely disconnects the battery from the load or from the charger to prevent catastrophic damage, as was explained before. But also in this type of diagrams we can visualize and represent also, for instance, soft protections. The soft protections will act as preventive measurements, and when the battery is approaching that dangerous boundaries, the BMS issues warnings and adjusts operation, for example, reducing the charging current or turning on the heating system, or for instance, turning on the cooling system to prevent that we get to those unsafe conditions. In applications where the safety and where the reliability are critical, for instance in electric vehicles, the BMS must include redundant protection to safeguard against failures of the primary system and the primary also monitoring system that take care of those protections. So redundancy basically will ensure that even if one of the layers of our protection fails, additional systems are going to be in place to maintain the safety and to prevent any catastrophic outcomes. Here we have one example that is showing the different layers that a system might have. Here in the first layer, we can see this dark green color that will indicate the area in which the battery should always operate, and this is the area where our battery operates safely. Then we have another layer that the boundaries are a little bit wider, and in this case these are the soft protections. This is an area in which the battery continues operating but requests already some to adapt the load, for instance, or to monitors and to send warnings to the system to prevent the unsafe limits to be reached out. Then we have the orange border that we can see over here, and this is the primary protection conditions. When the battery voltage, temperature or current crosses this border, the BMS takes corrective actions to prevent failures, and usually this is done by disconnecting the battery from the system and isolating the battery from the system. And then we can see that we include here a second border that is the red one, and this is the redundant protections. These are basically backup protection that will act in case that the primary protection system fails, or in case that system is bypassed. In that case, the red protection is secondary, usually under normal operations. This shouldn't, we never should reach that point, but if any of the measurements or the contactors or the BMS fails, that second layer will ensure that the system is still protected. So with this, we conclude this module, and to summarize it, we have reviewed the essential components, and we have also reviewed the functions of the BMS for monitoring and for protecting the system. As we move forward in this course, we will explore more advanced topics of the BMS, and we will understand better how all of this is implemented. So thank you very much for your attention.